Today we want to talk about the image method in electrostatics, and looking that, well, it can be maybe a little bit hard to explain. We are going to use an example to do it, but you need to know that there is actually a general equation that you can use to express this method that consists in expressing the electric potential, which is actually the objective of the method. Okay, we are going to express the electric potential as, well, the sum of the contribution of the electric charges of the system that we are dealing with, plus the sum of the potentials generated by some imaginary charges that we are going to introduce on the problem. In this case, these imaginary charges are going to be called image charges. Okay, so in this case is kind of like we are going to substitute the system that we have to another system of electric charges where we are going to introduce these imaginary charges, and then let's see what happens. And we are going to take into account that there are some properties of the initial system that we need to maintain to make the new system equivalent to the initial system. So for example, in this case we have first of all we have an electric charge Q that is located on a distance d on the x-axis. This distance is away from a conductive plane. Okay, it is an infinite conductive plane that has a sigma constant electric charge distribution. Remember that, well, it has an electric charge divided by an area. Okay, this is like a surface charge distribution because it is a plane. Okay, so it is charge divided by the unit of area. Okay, but in this case we will need to calculate the electric potential due to the contribution of the plane and the electric charge Q. The problem is that, well, this electric charge Q will change the charge distribution on the plane. Okay, because this charge Q has an electric field that will make an influence on the electric charges that are on the plane. Okay, so that means that this sigma is going to change. It is not going to remain the same just due to the existence of this external charge that we have. Okay, so we are going to propose that this system that we have can be equivalent to another system of just two electric charges, Q and Q prime. Okay, where Q prime is going to be the imaginary charge, and it is on it is away from the plane on a distance d prime. Okay, so just to make it simpler, we are going to have this charge Q prime here, the charge Q here, and this is going to be away on a distance d, and this is going to be on a distance d prime away from the origin on the x-axis. But we are going to erase the existence of the plane. Okay, the plane is no longer part of the system. So we are going to calculate now what will be the electric potential due to these electric charges now. So this system needs to be equivalent to the initial system that we had. Okay, perfect. So another thing that we need to mention is that, well, we have a plane that is infinite with a constant charge distribution. In this case, it is, well, this is another view of the plane where this is the z-axis and this is the y-axis. Okay, but we know that in this plane there are no electric currents. That means that the electric charges are not moving on the plane. So looking at the electric charges are not moving, the electric field on the plane is going to be 0. Okay, so that means that, well, if you remember, there is a famous relation on electrostatics that says that the electric field can be defined as negative the gradient of the electric potential. So if the electric field is 0, we can set easily that the electric potential is going to be constant. So that means that in this plane that has a constant charge distribution sigma, that means that the electric potential here is going to be a constant. But in this problem, for simplicity, we will take it equal to 0. Okay, so that is going to be important. Okay, perfect. So if we notice this equation, we know that, well, we need to sum every contribution to the electric potential for every charge. So that means that, well, the electric potential on the point P is going to be equal to, well, the electric potential due to the first charge, Q over 4 pi epsilon 0 R. Remember that R is the vector that points from the charge Q to the point where we want to measure the electric potential, plus Q prime over 4 pi epsilon 0 R prime, where R prime is again this vector that points from Q prime to P. Perfect. So what happens with this? Well, we need to realize that R, well, it can be easily found. We know that there is this relation here, R, little r minus dx, okay? It is very easy to notice that, well, this vector R, if we sum with this vector d in the x direction, we will get this little r vector, okay? So if we solve that equation for r, we get that r can be defined in this way, okay? Again, for r prime, we are going to get that this is going to be, well, r minus d in the x direction, and this is d prime, okay? This is different from d, okay? So this means that, well, r can be defined, and looking that little r is equal to x comma y comma z, well, r is going to be x minus d comma y comma z, and this is going to be x plus d comma y comma z, okay? But we are interested in the magnitude of these vectors, so that is easy to calculate. We know that r is going to be the square root of x minus d squared plus y squared plus z squared, and then r prime is going to be the square root of x plus d squared plus y squared plus z squared, and this is d prime. Okay, perfect. So we are going to substitute that on the electric potential. We are going to get that phi is going to be q over 4 pi epsilon 0, the square root of x minus d squared plus y squared plus z squared, and then plus q prime over 4 pi epsilon 0, the square root of x plus d prime squared plus y squared plus z squared. Perfect. And remember that we mentioned that at the point x equals to 0, well, we would be located on the plane. So that means that the electric potential is 0. Okay? So we can use that conditions to establish the next equation. The electric potential is going to be 0 when x is equal to 0, so we are going to substitute 0 here and here. So we are going to get q over 4 pi epsilon 0, the square root of d squared plus y squared plus z squared, plus q prime over 4 pi epsilon 0, the square root of d prime squared plus y squared plus z squared. Okay, so it is easy to notice that, well, we can set this equation to be negative this, okay, and we erase this 0. So we get this. Okay, perfect. In this case, well, remember that what we want to do is to find actually what is the value of q prime and d prime, okay, to make our new system of charges. So it is very easy to notice in this equation that the solution for this q prime and d prime, well, is just going to be that q prime is equal to negative q, and that d prime is actually d. Okay, so look, d prime is equal to d. So that means that we have kind of like a mirror effect on the system because, well, it is far away on the same distance that Q is. So that's why this method is called the image method. So because it is like watching the charge on a mirror, for example. Perfect. So looking that we just found Q prime and D prime, well, we can establish the final result for the electric potential. That is going to be phi of R equal to, well, Q over 4 pi epsilon 0 square root of x minus d squared plus y squared plus z squared, and then minus Q over 4 pi epsilon 0 the square root of, well, x plus d squared plus y squared plus z squared. Okay, perfect. So we just found what is the electric potential on the point P. What happens with the electric field? Again, remember that the electric field is negative the gradient of the electric potential. So for example, the x component of the electric field can be found with negative the partial derivative with respect to x of the electric potential. And, well, it is very easy to notice that this derivative is going to be equal to Q over 4 pi epsilon 0 times, well, x minus d over x minus d squared plus y squared plus z squared, just by taking the derivative with respect to x of this expression that we have here. And in this case, well, it will be minus x plus d over x plus d squared plus y squared plus z squared, and then this is going to be raised to the 3/2. Okay? If we calculate the other components of the electric field, we are going to get that Ey is going to be, well, negative the derivative of the potential with respect to y equal to Q over 4 pi epsilon 0 times y over x minus d squared plus y squared plus z squared to the 3/2 minus y divided by the same. Okay, it will be that. And the z component of the electric field is going to be negative the derivative of the potential with respect to z equals to, well, Q over 4 pi epsilon 0 times z over, well, it will be this, but negative. Okay, and here we are going to have minus z over this thing over here. Perfect. And recall that, well, when x is equal to 0, remember that we need that the electric field needs to be equal to 0. So when x is equal to 0, the denominators in these expressions are going to be the same. Okay, so that means that we are going to have y divided by something minus y divided by something, so that is going to be 0. And in this case, for the c component, is going to be the same. Okay, so this solution matches with the initial condition that we gave for the electric potential, so that is good. If we want to write that, that means that when x is equal to 0 on y and z, this is going to be 0. Well, this is for the y component and for the z component. Okay, so again, if we take the reference system here where the plane is located, this is the x-axis, well, we are going to have a component of the electric field that is going to be in this direction. That is the x component of the electric field. So the value of the electric field there, well, is going to be well, this function that we have here evaluated at x equals to 0. So what is that function going to be? So ex at 0, and on any point y comma z is going to be, well, the result here, but evaluated at x equal to 0. So that means that we're going to have here q over 4 pi epsilon 0 times negative d over, well, d squared plus y squared plus z squared to the 3 halves minus, well, a d again divided by the same, this thing over here. Okay? But this is going to be 0. So that means that we have d squared here. Perfect. So we easily notice that we are going to have minus 2d divided by this, and that 2 is going to cancel with this 4 that we have here. So we are going to get that this is minus qd divided by 2 pi epsilon 0, and then d squared plus y squared plus z squared to the 3 halves. Okay, perfect. So that is going to be like the normal component of the electric field on the plane. Okay, Ex evaluated at 0, y, z is like the normal component of the electric field. Perfect. And remember that, well, there is a very famous result in electrostatics that says that, well, the electric field due to a conductive infinite plane on a certain point P, well, it can be calculated as, well, E equals to sigma over epsilon 0, okay? Where, well, we are going to calculate the electric potential on this point due to a plane that has a constant surface electric distribution, okay? So that is the electric field of this plane here. So that means that this equation needs to be equal to this term that we have here. So that electric field needs to be the same. Okay? But that equation tells us that sigma can be calculated as the electric field times epsilon 0. But we have just calculated that the electric field is this expression that we have here. So that means that the new surface distribution is going to be sigma equals to, well, negative q times d times epsilon 0 over 2 pi epsilon 0 times d squared plus y squared plus z squared to the 3 halves. Perfect. We see easily that this can be cancelled, and this is going to be negative qd divided by 2 pi times d squared plus y squared plus z squared to the 3 halves. So notice, we have just found a sigma distribution that is not a constant. Okay, it is very easy to notice that this now is a function of y and z. Perfect. So the electric distribution can be found now with this function, but it will be different on some points of the plane. Okay, it's not going to be the same on the origin or on another different point on the plane. Okay, so another thing that we could ask that could be interesting in this problem is that, well, what is the force, the electric force acting on the charge Q? Well, we know that we have a plane that has a non-constant charge distribution. Well, this is going to generate an electric field on the charge Q. That electric field will make this charge Q to feel a force, okay? So that force can be easily calculated because we already know what is the value of the electric field. Remember that, well, the electric field on a distance x is this expression that we have here, but the charge Q is located at x equals d, okay? So if x is equal to d, well, it's easy to notice that we are going to have here d minus d, so this is going to be 0, so this term is going to cancel. It will be 0. And here, if x is equal to d, we are going to have d plus d to d, okay? And here, again, we are going to have 2d, okay? So if we take that expression and substitute the value of x equal to d, we are going to get the next. Okay, so we are going to have this expression to calculate the electric field on the charge q. So again, remember that the charge q is located on the point d, 0, 0. So that means that the values of y and z are 0. That's why I wrote these zeros here. Okay, perfect. And remember that we saw that the first term was going to be equal to 0. So that means that the electric field on the charge q, which is this, well, it's going to be negative 2 times q times d divided by 4 pi epsilon 0, and then these 2 will cancel with these 2, and we are going to have 2d to the third power. So this is going to be equal to negative q divided by, well, 16 pi epsilon 0 d squared. Okay, perfect. So this is going to be the electric field. And remember that we can easily calculate the force on a charge q that is under the influence of an electric field E as, well, the charge q times the electric field. So that means that the force on q is going to be negative q squared divided by 16 pi epsilon 0 d squared. That will be the force acting on q. Perfect. So we just calculated what is the new distribution of charges, what is the force on q, and what is the electric field on any point of the space, well, due to the charge q and the conductive plane. Okay, perfect. So I think this is a good place to stop the video, and if you have any question, well, make it on the comments.